Hello. Good evening, team. Am I audible?
Yes.
Okay. Thank you. We will give 3 more minutes for the others to join, and we will start sharp at 3:05 p.m. Please stay tuned till then. Thank you. So, welcome back. Good evening, team. Thanks for your time and taking out your time and from a busy schedule and attending this webinar, technical webinar on hidden features of Keil Simulator. Keil is a very well-known and popular tool in the embedded market, embedded domain, and many customers are using this user-friendly Keil software tool for development of the project based on any ARM-based processors or any ARM-based embedded systems. So today the topic is about simulation. So simulator, at present, I guess the users don't use simulator feature much because they tend to develop their program and test the program directly on the ARM-based hardware board, connecting in JTAG debugger. But today's webinar was to know the features of simulator, why simulation is important, and how it will help you. Okay. So we will start up with the webinar, and before starting up, let's keep this webinar interactive. Please feel to drop all your questions on the chat window, and please cooperate by keeping your mic muted. Put the questions on the chat window. At the end of the session, I'll certainly come to the questions which are being posted on the chat window, and I'll try to answer them. So let's start with the webinar. The agenda I have planned is first I'll be going through the slides and then I'll be showing practically on the Keil ID. Let me share my screen. So hope the team is able to see my screen. So coming to Keil Simulator, the simulation word stands the same, terminology remains the same. Simulation is something, if the team is not aware, or kindly bear if the team is already aware about the simulation, it will be a kind of brushing or reiterating the knowledge or updating the knowledge. Simulator is something where you want to test your program, what you have developed on your Keil IDE, the C program or an assembly program, you want to test it. And you don't have the hardware in your hand. So like if you take a real-time application, you're working on a real-time project and software team is separate, hardware team is separate, the current scenario, what I have seen, what I've been observing though. So we have separate team for software and separate team for hardware. So software team's main onus is to develop the software for whatever the hardware team develops. And we understand a hardware development of a hardware board involves a lot of steps and the procedures, and so software team has to wait until the hardware board is available to finally test their program how it is working. This is certainly going to extend the SDLC, software development lifecycle. So to cut short this SDLC, and first thing is, why should anyone reduce this time, software development lifecycle? Because it's ultimately coming to getting the product to the market faster. So as soon as you get the product to the market faster, you'll be able to win the market, you'll be able to capture the market, or you'll be able to take the business from the market available. So if I give an example, phones, mobile phones, everyone has it now. Smartphone has become part and parcel of each and everyone's life, and without smartphone, you can't even think of spending a day, spending an hour, or spending even a half an hour, 30 minutes. So smartphones, if you see, we have variety of brands. We have Xiaomi, we have Samsung, we have Sony, I guess, Realme we have. So there are various brands. We have Apple iPhone. So we have various brands available in the market, though Apple, we are not comparing here, just I told the brand. Suppose if you say Realme, Xiaomi and Samsung, all are Android-based phones, smartphones. And all these companies are working on developing a smartphone. Let us as an example. So whoever releases the smartphone first to the market, so obviously customers are going to purchase that. Until the company does some product advertising saying that the next upcoming model has so and so features, it has good camera, resolution, whatever it is. So if depends on the customer's decision also. Again, if it is like branded, if the customer wants to go only with the branded, they'll wait for that particular brand of phone to available in the market. But for new users who are not even the users of the mobile phones, they will tend to use the smartphone which was released to the market first. And thereby, suppose example, if Samsung is releasing the phone to the market quickly, and Samsung is also giving the same features in similar to Realme and Xiaomi, then still Samsung will occupy the market because they brought the product to the market first. So ultimately, this is about competition, winning over the competition. And in embedded, you see there is a competition for sure. Every product, every company manufacturing a product, there will be some other company manufacturing the same product. Okay, so always it's important to get the product to the market, to capture the market, because finally what is the motto, what is the reason for developing a product? Basically to sell it in the market and make the profit out of it. So bringing product to the market quickly and as early as possible is very, very, very critical and very important. Simulation plays a vital role here. So what does the simulation does is, even before your hardware is ready, software developers can develop a software in the Keil, and they can test it on the simulator. So simulator is a virtual target. Means there is no hardware present, but still you can test all the functionalities of your code what you have developed. Okay, in that direction, ARM has focused, or we're investing highly on the resources to develop the simulation models. So whatever simulator features I'm showing is for your Cortex and MCUs, but if you go for higher end Cortex, application specific, Cortex are real-time specific. When Cortex M, you have M23, M30, which is the latest version where there are not much MCUs or simulation support is there. For that also, they're coming with the simulation models. My next webinar will be on the showing this how to use the simulation model fixed virtual platform, which I'll be talking. Maybe next month I'll have one more webinar on FEP. So today is the simulation part. So now I have told that without hardware, you will be testing your software. So how this will help in getting the product to market fastest? By the time hardware is ready, software program is ready, and once the hardware comes into the picture, software team can download the program to the hardware, debug it, test it, whatever it is, and they can get the product to the market faster. So having been told this, how do you simulate? Because when you may ask, it's a real-time application and so many peripherals, higher end peripherals, everything is included in my application. How will I simulate without hardware? And you may ask, okay, in my application, I'm expecting some input from the external world, maybe some sensor, some you are designing a sensor or an ADC sensor, whatever. I'm just giving you an example. It's expecting some input from the outside device, other device or outside application. Okay, maybe I'm not telling all the features can be simulated, but yes, at least depending on your application, 80% of your product, your software can be tested and simulated. Okay, so what is that main thing? Usually simulation means the mindset of the end user is instruction set simulator. True. Keil not only give instruction set simulator, but it also helps you, it also gives you the simulation support for the peripherals. Peripherals can be ADC, DAC, timer, even interrupts, CAN, I2C, SPI. All these communication peripherals can be simulated. So how they can be simulated? Through virtual registers. So what are virtual registers? As the name suggests, virtual means these registers are not present in the processor. So you may ask me, madam, why this virtual register is coming into picture? So hope the team is ready to admit that communication peripherals, whatever we use in our program or in our hardware, they are all configured through pins. Hope you agree. Suppose you want to send a serial data, you need RxD TXT pin. Suppose you are using I2C, you need SD and SCL, that is data and clock signal. Suppose you are using SPI, you require 4 pins: MISO, MOSI, slave select, and target clock or slave clock, whatever. So these communication peripherals, how do you write the program? You, whatever data you're sending, you're configuring this peripheral to send the data, it is sent through pins. So they are called communication peripherals because they send the data through the pins of the MCU. Okay, so how do you test the data which is going through the pins of the MCU? How can anyone tell how can you access the pins of the MCU in your software? Impossible. Because suppose I'm writing program for an I2, I2C. I know the peripheral theoretically how it works. But how do you program that in an embedded product, embedded processor? It is through registers. That is peripheral specific registers. So for I2C related, whatever registers we have for that particular MCU, we'll use those registers and we will configure that particular peripheral. But there is no way you can access the microcontroller pins. Okay, so to access this microcontroller pins, to give the input to this microcontroller pins, or to send the output to this microcontroller pins, Keil has given the feature called as virtual registers. And the name suggests virtual means these registers are not part of the processor, they're not part of the MCU, but these registers are specifically given for simulation purpose. Okay, so also Keil has given a lot of debug functions which will help you to write the simulate for this complex peripherals. Okay, so the microvision simulator gives you simulation of few of this. I have written here UART, I2C, SPI, and CAN. These are all communication peripherals. So now don't ask me USB and Ethernet higher end communication peripherals. Keil has also simulated that, but they have not, because there are higher end peripherals that operate at megabits per second speed and all. So no one has used simulator for that higher end peripherals. Okay. So simulation of these peripherals, that is UART, I2C, SPI can be done through signal functions. So now one more terminology is coming into picture, which is signal function. So one terminology which you have to capture from this slide is virtual registers. Okay, virtual registers are specifically given by Keil, by the Keil IDE for simulation of your communication peripherals. Okay, next is signal function. So we'll see what is signal functions. So signal functions are the functions which operate in the background. So in your foreground, on your Keil IDE debugger in the simulator, your main application, what you have written, will be executing. On the background, these signal functions will be executed. Okay. So you may ask, if the background my signal functions are executing, how will my foreground or front application, my own application executes? This is done by giving a delay. That delay is called as T-watch. So T-watch here is, we can give the delay in terms of seconds, in terms of watch cycles, in terms of machine cycles. So T-watch is based on the machine states. So similarly, if you want to give a delay for a few seconds, you can give S-watch. Okay, so there are different types of watch here. So, but there should be some delay when you're defining a signal function. So then you may ask me how to write a signal function. Signal function is a simple C program. Like how you write a simple C function, similarly, we can write the signal function. So signal function, you can write it in Macrovision editor itself, but you have to save it with the ini extension, .ini extension. But at the time of demonstration, I'll come to that. So one thing to note, main thing is we have to give a delay. Once the delay comes, only the background execution of the signal function stops and foreground your main application will execute. Because the background function also has to execute, because this is giving input to your communication peripheral. And because you've already written program in your application, in your Keil IDE, for whatever input that comes to the communication peripheral, what is that particular peripheral has to do. So that is what you want to simulate, and that is what Keil is facilitating you towards. Okay, signal function, this is how it starts with a signal word strictly, and it should have void, it should not return any parameters. Function name, you can pass the parameters to it. Okay, so example here you can see this particular function, signal void stuff s not in, is here we are simulating the receipt of the character from the UART. So usually in C function, how do you transmit the data? We write a printf statement. Any embedded application, if you take not only for any embedded application, if you want to send a data through UART, we use a printf function, or we use a put character. In this function, we are trying to simulate get character. Means I am trying to check how the UART operates, my peripheral operates when the data is received by it. So receiving is what? UART has to receive data from the external world, from external application, external device. So to avoid that connectivity with the external world, I directly give the received data in S not in. So S not in is a virtual register which will simulate whatever data which is coming to the UART. And you can see here we have given delay. Okay, we will discuss about more of these signal functions when I demonstrate the same in Keil IDE. So any questions, please feel free to put it in the chat. So similarly, this is an example of an ADC. Like previous example we saw was UART. Receiving, here this is ADC. So ADC, again, you know, microcontroller has on-chip ADC, means you can give analog inputs to it. So how do you give analog input? Through again the pins of the microcontroller. So for here we have to, yeah, Lakshya, please feel free to put the questions. I've seen your question, but please be patient enough to come. Let me complete my session, and I'll certainly come to your question. Thank you. So yeah, so what this ADC we have to give analog input to a ADC peripheral. So you have to give an input to the ADC pin. So how to generate we have to give the analog input. So what we will do is, in C function itself, we'll write an analog signal function which generates a signal pattern. Can be sinusoidal signal, this one triangular wave, square wave, anything. You can write a C function, script function, which will generate the analog signal at that particular pin of an MCU. So you may ask me if that particular ADC has what else? The number of inputs is 8, or number of inputs is 12. So that time for each input there is a separate virtual register. So you can see here, for example, this particular microcontroller, whatever example they have shown, they are not showing the microcontroller, but this particular controller, whatever this particular AD converter is shown, it has 4 inputs: AN0, AI in 1, A input 2, A input 3. So you can give input for any of this particular microcontroller pins. So I can give to this one 0, 1, 2, 3. So whatever the virtual register I used in my C script function, for that particular pin, it will generate a waveform. And I have already written a program for accepting the input. ADC is configured such that it will receive the analog input and give you the digital output. That particular thing I have written already in my C program. Only thing, how do you simulate ADC? We need an input, analog input, right? Because there is no hardware. So you give the input through virtual registers. And these features make the Keil simulator unique. Until the date, no other competitor or no other vendor has come up with this feature of virtual registers and simulation of peripherals. Now coming to digital input. Digital input is, in the microcontrollers, we have GPIO pins. And these GPIO pins, what happens is, if the particular processor has many functionalities, many peripherals, but the number of pin count, they want to keep it less. So what the silicon vendors do, silicon vendors means semiconductor vendors do, they multiplex the functionality of the GPIO pin with various other features. Like, for example, they may multiplex the GPIO with the UART transmit or UART receive, or it can be multiplexed with external interrupt, or it can be multiplexed with a I2C or with an SPI. So this way the microcontroller pin count is maintained low, and the particular microcontroller becomes more powerful because it has all the peripherals which is required for your application. Okay, that is where technology is going towards. Okay. So this one I'll be demonstrating it, and because suppose particular port pin is also connected to the XL interrupt, so I can also simulate my interrupts here. XL interrupt, XL interrupt, how it generates. Usually when you put up a press a switch, when you toggle a particular like a joystick or something. So because there is no hardware, I can still make that particular pin, because how the embedded application works for interrupt is, the application toggle waits for that particular pin. It keeps on polling for that particular interrupt pin. Once that particular pin goes high or low, whatever, depending on the processor. Let's take low example. As that particular port pin goes low, processor will generate an interrupt to the processor. So that is what we are doing here. We are directly, you can see here, it gives you the even pins access. You can directly click on a particular pin where you want to generate an interrupt, and it triggers an interrupt to the processor. This again here I am simulating the interrupts as well. Okay. Next comes a logic analyzer. So what I'll do is I'll stop till here. No, I'll continue, because logic analyzer also can show whatever analog input we generate through signal functions. We can see that in the logic analyzer as well. Okay. So logic analyzer, what it does, it's a graphical analysis tool. I'm not sure whether the team who is part of this on this bridge has used this feature. This logic analyzer feature is available for both simulation as well as with the hardware for Cortex-M specifically. It's you see graphical analysis of your application. or whatever variables you use in your program, or the virtual registers. Whatever virtual registers used in your C script can also be added to the logic analyzer and you can see it. But there are some restrictions, means it cannot show you the CPU registers. CPU registers means your core registers like R0 to R15 or some register specific to the CPU core. And it cannot show you the peripheral registers. Suppose you are configuring ADC, you cannot see the ADC register value. So there are some restrictions there.
Hello. Hello.
Hello.
This is Kumarasamy Edigonda.
Kumar Swami, can
Hello.
you please put your questions in the chat window?
I'm trying to log in into webinar, ma'am, but I'm unable to log in using my mobile phone. I entered mobile phone number, but not accepted, and also I tried to log in with using meeting ID and password, but I unable to logged in to attend the webinar. Webinar.
But then how you have joined in audio mode now?
Meeting ID and password sent to my WhatsApp number by one of your colleague maybe. But that also I used, and using mobile phone I'm trying to log in.
Yeah, fine, but because you are talking over the WebEx, I believe you have already joined.
Joined, ma'am? I got already joined, but I'm not visible. App I installed. That using that app also I can log in. Can I try to log in using that app?
Yeah, please go ahead.
Okay, ma'am. Thank you, ma'am. Yeah. I will try one more time. Okay, ma'am.
Yeah, thank you. Sorry for the interruption. Okay. So logic analyzer can be used along with the simulator, or you can also use this feature along with the trace feature. Regarding this trace, I have conducted many webinars. Interested team member, interested attendees can visit our GISA site, and there are recorded videos. You will get the link over YouTube and you can watch them. So with the help of trace also, you can see real-time signal information. Okay. And so this is how logic analyzer shows up. So you can see ADDBG is the variable which we used in our program. AD last, ADDBG, these are all the variables. So whatever variables you use in your program, you can still see them. And whatever virtual registers you use, also you can see them. So it shows here a log input. This is a variable value. Okay. And here you can also monitor the signals graphically, but you can also analyze your code along with the logic analyzer. So how is that? Here you can see the option jump to code. So there is two cursors here, red and blue. So you can place any cursor to any point in this logic analyzer and give your jump to code, and the simulator will take you to the particular part in the C program which made this transition in the signal. So you can easily analyze even your code along with this logic analyzer. So you can see any waveform, any value in analog state, bit state, zeros or ones, or analog state. Okay. Next, coming to code coverage. So what is code coverage? As the name suggests, it shows the information on what are all the parts of the code which is covered by the processor. So here you can also see, basically code coverage shows you what all the C functions which are defined in the C program, whatever you're trying to simulate. Suppose this particular program is for measure, and you have all these modules. These are all C files: getLine, mcommand, measure, serial, retarget, getLine.c, setTime.c. These are all C files. Your function, getLine function, setTime function. So it also tells how much percentage of that particular function has been executed. Okay, so you may ask me why code coverage is required. Yes, in simulation, code coverage may not be of much use, but yes, at least we can find out which part of your secret is executed. But this plays a critical role if you're getting your product certified for any functional safety applications, or if your product is going to any industrial automation or automotive or railway or medical. So this code coverage ensures that it'll make you get the information what are all the paths or what are all the C statements the particular processor has executed. Okay, and the code coverage should be 100% to get your product certified. So this code coverage along with the trace information. So trace here I'm talking about is instruction trace. Instruction trace is the JTAG debugger which you connect to your hardware, because trace cannot be possible in simulation in real-time trace, so that we have to connect a JTAG debugger. The debugger should have intelligence to know the data which is coming to that instruction trace port, or we call it as ETM port, trace port. So what that instruction trace does is whatever are the opcodes the processor has executed, it captures all those information and sends to the ETM port or a trace port, and the debugger, which is capable of understanding this information, captures it and shows it on the tile ID. Okay, so this real-time code coverage information is very much required for getting a product certified. I'm not saying this is the only thing, but this is one of the mandatory thing, one of the prerequisite for getting a product certified for any of the functional safety applications. So once you see that only 80% of the program is 80% of a particular function is executed, so other 20 you can always guess, because if the particular function has a conditional statements like if statement, for statement, then if condition is true only, it will work. The if part, else part is ignored by the processor. So that time we will use a unit testing feature, or we use the utility tool which is capable of creating a test cases which will modify the condition itself. And once the condition becomes false, processor can take the else path also. So why this is required? To see that all the paths, even if it is condition also, if else path, everything has to be covered by the processor. Next is a system analyzer. System analyzer is again a graphic analysis tool. Similarly, you can take it as a logic analyzer, but one additional feature it has is one additional feature it has is it gives you the power consumption. If you are using Ulink Plus, this is a JTAG debugger from ARM only. Ulink Plus helps you in programming of the flash of the processor or MCU and debugging the code which is running on the hardware. In addition, it also can do the power measurement. So whatever the data, voltage and current rating from the Ulink Plus on your application, on your product hardware, you can see that in system analyzer. You can see all the exceptions. See, logic analyzer doesn't show exceptions. It doesn't show power measurement. Okay, it does show the virtual registers or variables. And RTOS, thread events and status. RTOS is your Keil MDK also comes with the RTX RTOS, and if you're writing any threads or tasks, status of those, because though it will multitasking, only one task will be executing at a particular time. So all those task related information, everything you can see that in this system analyzer. It's like a single tool which captures all the information. This is how it looks. So you can see a system core clock, you can see consumption, this is current and voltage consumption of your application. Exceptions, we have supervisor call systic. Basically, systic is, this is a core, we have 24-bit systic timer or counter which takes care of this can be used as a timer, general purpose timer. It is inside the processor core. Supervisor call is for RTOS application. Supervisor SVC call is specifically for RTOS application, because switching between the task and all happens from the user application to the kernel through the supervisor call. Supervisor is like when the user wants access to the privileged resources of your CPU, then they call it through supervisor call. It can be both ways, because if it's an RTOS based application, yes. Because this RTOS based application, you can see it's many threads also you can see. So this is how system analyzer shows up. Okay, so now I'll come to this demonstration part, and after demonstration, I'll take up the questions. Stop sharing. Share. Okay, hope the team is able to see my screen. So one by one we will see. So first we will see the virtual resistors. How do you see the virtual resistors? Because virtual resistors, as I told, it is for simulating your communication peripherals. Not that all the MCU has the same set of communication peripherals. In some communication, some MCUs may not have I2C, some may not have SPI. So depending on the processor, the virtual resistors are being designed by the Keil team or ARM team. So for this webinar demonstration, I have taken example projects. I have not developed anything explicitly, separately anything. When you install the Keil software, you will get all these examples by default, okay? So I have selected a Blinky project, which is for 1700. 1700 is a Keil MCB 1700 board, which comes with a Cortex M3 MCU, LPC 1768. So this particular program can be executed by loading into the RAM of the device. We can load it to the flash of the microcontroller and you can test. But because I want to show you the simulator features, I'm showing in the simulator. So just open the project and build it. And here you can see. So this particular program, let me explain you. I'm not explaining the program in detail. I'll just tell you this particular Blinky program, what is the principle on how it works is this board has a onboard ADC and it has a potentiometer which is connected to one of the analog inputs of the ADC, and when you vary the potentiometer it gives the analog input, and the program what you have written will convert that to digital output, and that digital output is what we send the digital output data printf statement through the UART. Okay, so now we are simulating the ADC here because we want to show the simulation of ADC functionality. So here, this is a INI function, as I told. We'll be writing a signal function, and that it should be like a normal C function, and it should have a .ini extension. Okay. So you can see here, I have given the function name analog. You can give anything. It should start with the word signal strictly. You're not passing in the function should not return any value, and the limit. Okay, so this is the LPC 1768 has a 12-bit ADC, and it can this ADC is operatable up to 3.3 volts. So I can give the limit as 3.3 volts. Okay, why the limit is because this particular function generates a staircase waveform as an analog input to the ADC. Okay, like a normal C function, until you call this function, it will not execute. So I am calling also this function analog 3.3. Analog is a function, and the input to this function is 3.3. Okay, and because this is a continuous process, it will start from 0, and in the steps of 0.1, it goes up to 3.3. Once it reaches the 3.3, it checks the condition is 3.3. Again, it comes down with. It decreases with the steps of 0.1, comes to 0, again it goes to 3.3. So we have kept this in infinite loop. So volt 0 is actually the input value what we are giving. Less than limit is, your limit is 3.3. Now AIN2. AIN2 is my virtual register which is connected to the analog input 2. So in my program, the potential on the hardware, the potentiometer input output is connected to the AIN2 of the ADC of the LPC 1768 MCU, and have given here delay, and then I am incrementing it with 0.1. So in steps of 0.1, it becomes 0.1. It will become, then it go to 0.2, 0.3, 0.4, like that. It goes up to 3.3. Okay. So once it becomes to 3.3, you can see volts equal 3, limit is 3.3, and then it will decrease in the steps of 0.1 and become 0. This is my analog input in staircase. If you want, you can also generate sinusoidal. We have square wave generate, square wave, anything you can generate like using this script function. So now we will enter the debugger simulation. So you can access this D from, close this so that I can open it and show you where they are located. Okay, you can access this from start and stop debug session from the debug menu. Okay. So this program is a normal C program. Now to see what are the virtual registers, we use dir. See, as soon as I give V, it will only tell you VT register. So this shows me what are all the virtual registers for the peripherals of this particular controller. I will quickly go through. Okay, this is for USB clock. USB clock. This is for all ports. Ports is to access the pins of a port. S0 in, S0 out is for UART. This has 3 UARTs. S0, S1, S2, S4 rather 4. And this is all for CAN. For simulating CAN, 2 CAN ports. SPI, it has I2C, SPI, and all the analog inputs. So depending on the processor what you have selected and what are all the peripherals which you can simulate, ARM has given those virtual registers. Okay. So because it's a C function, there is an also after entering the simulator, because we are users and we tend to do errors or mistakes, then this function editor is there. This has the option of compile. So this will compile and see if there is any errors. Suppose because you're using debug function or something and all, if there is any error, it will highlight there. So now if I compile also, it will tell me function analog is currently in use, because as soon as I enter the debugger, this function is already invoked, because in the INI file itself, we have called that function. Like a normal C function, until you invoke it, it will not execute until unless it's exception or interrupt handler. So here I'm invoking analog function, signal function with input 3.3. So that's the error. Otherwise, there is no syntax error here. Okay. So now we will see. I'll show you logic analyzer. So logic analyzer here, it shows the AD last. This is your whatever is the digital output of the ADC, because input I'm generating to signal function. So I have to see how ADC is performing, how it is generating the digital output, whether it is generating correctly. Okay. So now if I run the program, you can see staircase mechanism started. All if I click, it goes. So this is how it generates a staircase waveform, and this is my analog input. Okay, so I want to see the digital output now. So once I stop the program, it shows the digital output. Okay, because on the fly it will not update. Once you stop the processor, it shows the digital output. At any point of time, and if you want to see, click jump to code. It takes you to that particular line in the C code. Okay, and the same thing you can see the output in the peripheral. If you go to peripherals and you have ADC here. Okay, so this particular ADC of LPC176 has so many registers. So here I'm giving input to analog AIN2. So you can see here input value is 1.1 because I stopped the processor now. At that point, whatever the input it was given, it's showing here. And this is your digital output. I'll show you. This is your result. 30. ADC last I should add. So when I run the program, so you can see here, this continuously updates. It goes up to 3.3 and then it again reduces. You can see here. It is now going to 0. Now it increases to 3.3 and again it becomes to reducing to 0. So that is how this particular analog function works. And this is your result, digital value. The same thing you can see here. Okay. So this is our memory window. So this is how you simulate the analog input. Okay. Now I'll show you how do you simulate the interrupts. So there are many examples given on Keil site. I can quickly show you. I have to share the screen. Share. Do you see my screen?
Yes, it's visible.
Okay, thank you. So here I wanted to show you. See, signal function. Suppose if I go to analog input, they have also given example. This is the whatever I've given is your sawtooth signal. Similarly, you want to generate a square wave. So if you click here, you will get that function also. This is how it is generated. So you get a lot of information on Keil site also. I'll just quickly show you so that the team should not wonder how do I generate a square wave or how do I generate sinusoidal wave. So this is how it is. This is on the Keil site. Let's go back to our Keil ID. So this is how it shows your ADC. And now we will see the interrupt. So the interrupt here is, this particular example is given by the MX team only for Keil board. And we will just build this and enter the simulator. So here, this particular Excel interrupt 3. Can you please mute? Slanny, please mute. Okay, thank you. Just a second. So here one more feature you can see, buttons. You can see what is this button. So what is this button? Here this is a signal function which is given by the Keil itself for generating the interrupt. This is your signal function. I'll show you that signal function quickly. Debug function editor. Okay. So port 2, because port 2.10. P2.10 is where the Excel interrupt 3 is connected, because this particular pin is used as Excel interrupt, or this particular pin is multiplexed with EINT3. So it's written for that. And here we are pushing that particular pin low. So we're giving the whatever this function. Port 2 is my virtual register for accessing the port 2 pins of the controller. So to access this P2 pins of this GPIO2, so you have to, that is the simulation. This is the virtual register for it. Okay, so we are giving a delay and giving the input. We are enabling the interrupt. So now when this is the NVIC, nested vectored interrupt controller. So this particular NVIC, depending on any device, it will have a interrupt controller. You open that, and I have all the peripherals of the controller. What you are simulating here can see here in the peripherals menu. So from here I have open the core peripherals, NVIC, nested vectored interrupt controller. Okay. So here my interest is to see Excel interrupt 3. Okay. So when I run the program, you can see all this enable, everything will be done. So you can see interrupt is enabled. Okay. But it is not active because interrupt is being enabled for the processor. To tell the processor that this particular application has Excel interrupt 3. So we have to trigger the interrupt now. How do you do that? You can do that by this button. So once you click this button, then it will toggle the LEDs. LEDs are connected to 24 to 31st pins of the port 1. They are connected to LEDs. So it will move the LED to the left or right. So this will trigger an interrupt. So I can show that by putting a breakpoint here. So reset. See, as soon as I press the button INT0, it will come and stop at the interrupt 3 handler. So that indicates this particular function, P2 point, this particular button function has made the P2.10. You can see 8, 9, 10. P2.10 is made low. So it triggered the interrupt to the processor. So this is a interrupt handler for that particular interrupt. So this is how you can simulate your application. So you button INT0, I could have also directly given by push INT0. I could have invoked the function. See, you can invoke the function from the signal function itself, or you can invoke it in the directly here. So I'll show you both the options. So now this is invoked through button. To make it more user interactive, ID Keil has created a button here. Okay. So what I'll do is I'll show you. You can create buttons like that any number of types. See, this is the define button INT0 push into 0. So when you click that button, what is the action the IDE has to take? What is the action the simulator has to take? That is what is given in this button. Okay, so now what I'll do is button kill button. Kill. So as soon as I kill, it show me function or button. I'll give button. Kill button number. So you can see number is 1. So once I kill the button, you can see it's gone. So I can define the button, kill the button, means all these are to make it more user friendly, interactive, to show what all features Keil Simulator has. So you can define it, define button. Okay. So what is the button name? Button 90 was 0 was there. No, I'll give it as external interrupt. Need not we have to give the same thing what has given. So when I click the button, what is that it has to do? It has to execute. What is that function? Function name is push underscore INT0. Push underscore INT0. See. So now I created a button Excel interrupt here. So like that you can create a button. So if you don't want to create a button, you have to invoke it from the command window directly. Suppose if I give kill button 1. Okay, and I'll reset this and I'll run the program. Okay, it will not. Okay, it will not generate any interrupt. Okay, because I have to trigger the interrupt. So for that, what I'll do is I'll give push underscore int 0. It's a signal function. See the function correct. Okay, this function is there here. I'll do one thing. I'll just comment this. And signal function, whatever you define in the INI file, you have to give it here in the debug. Under the simulator, you have to give it here, initialization file. Button is coming. So like we did for analog, we can call it in the signal function itself, or we can call it from the, we can do it from the button. So both the features are there. And once you click here also, it shows Excel interrupt 3 enabled active. As soon as I click that particular P2.10 low, it will show you active. So active means it will alert the processor that Excel interrupt is generated. This is how you can also simulate your GPIO. Okay. So next we will see. So we'll see view analysis. So all your logic analyzer, code coverage, system analyzer, whatever I showed, everything is in analysis window. So that will open that analog project. So we have that. So I have code coverage here. So you can see here, main function. You have 3 conditional jumps. It will also tell you 80%, 84% of the code is executed. Why? Because 3 jumps were not fully executed. So all this information it shows, and with the help of unit test cases, you can easily modify those conditions. And see that those conditional jumps are also executed. When you're executing the program, it will not update. When you stop it, it updates the information. So you can see LED lit on, everything is executed 100% because there is no conditional jumps. There is no conditional statements.
चलो wait I'll exit.
Okay, then we'll see system analyzer. So system analyzer here, because I have not created a U-link plus or something and there is no interrupt or exception. So you don't see, you just see only this data watch as I showed. Otherwise it is any RTOS application, it shows RTOS threads, it shows power consumption, voltage rating, everything it shows, and it also shows the exception or interrupts. So this is about the features of Keil. For Cortex M, we can take it as M3 or M4. But for higher end, I'll come with the next webinar for FVP, fixed virtual platforms. That will be an interesting topic as well. So that brings me to this end of the demonstration and my presentation. So now it's time to take the questions. Okay, so I see only 4 questions. So team, this is a time to ask the questions. So feel free to ask, even it's a basic question, get it clarified. And if you don't want to ask now, I'm always available. I'll share my phone number and email ID. You can reach me at any time. So now coming to the question of Christina, is not is not only for UART RX? Yes. It is reserved for UART RX only. If you all want to simulate the transmitting UART TX, then it is S not out. So anything for receiving is in, S not in. What is S not in virtual register? Lakshya Bharadwaj. This virtual register is basically to simulate how UART responds for receiving the data from the external device or external application or an external world. So because this simulation we are talking about and we are not having any hardware and still want to see how UART responds, the program what you have written, how UART, whether you'll be able to simulate the receiving of the data through UART. So this particular virtual register is specifically helpful to simulate the UART peripheral. But code coverage in general can never be 100% right. Yes. Christina, you saw the demonstration when I gave code coverage. Wherever in the function C functions, when there is no C conditional C, there is no conditional jumps. Because for our processor, whenever there is a condition, a statement comes, the processor has to jump depending on the condition is true or false. So yes. It is called as conditional jumps. So if the function has conditional jumps, then obviously you will not get the processor to execute that function 100%. Okay, but we can always ensure that suppose if the condition is true, processor executes the if part, but using the unit cases, we can still make the condition false and make the processor execute else part. So this particular is called as MCDC, Modified Condition Decision Coverage, and this is a key requirement, key criteria for any application which goes to avionics has to certify for. That is for DO178B or really freight applications or avionics application. MCDC is very much critical, very much required to ensure processor takes all the path. Okay. Is there any possibility to record the change in the values of virtual registers and then end register value? Simhadri Prithvi. If you're still part of this session, can you reframe the question? Sorry, I'm not getting your question. Change in the values of the virtual registers. What is the necessity of recording? Sorry, I could not get your question. Can you please reframe the question for me? Bhavani, which Keil version need to use simulate ADC, LED, etc.? Good question. Okay, Bhavani. Keil, the latest version of the Keil which is available for the download from the Keil site is 5.36. Okay, for that you have to download the legacy support for Cortex M. If your question is about ARM7, you can simulate the same things whatever I showed now, virtual registers. You can do that for even ARM7. You can do for ARM9 as even for Cortex M. Okay, so you have to download the legacy pack for ARM7 and ARM9 from keil.com/pack. Okay, next. Is it possible? Yes, I'll share my phone number. I'll put that slide itself. Hold on a second. I did create it. I'll just share the screen. Okay. So hope the team is able to see the screen, and this is my email ID and contact details. So feel free to check with me. It's the chat option. Okay. Next. Okay. Sorry, one question I missed, Christina's. The simulator feature is available in Keil Macrovision from light version onwards, or it requires Essential or Plus. Good question, Christina. See, this particular simulator features works in even the light version. Even the light version is nothing but the demo version of Keil, which is code size limited to 32 KB. Irrespective of the license version, it need not be Essential, Light, Pro, anything, but it works even in demo version. So needless to say, it works with all the editions of Keil. It works with light version, it works with Essential, Plus, Pro, everything. Lakshya, my contact details are on screen. You can note down. Is it possible to simulate UART, DAC, and stepper motor? Yes, ADC and DAC. I told you it can be simulated. UART can also be simulated. I showed you the function S0N, S0in, which is for receiving, or S0 out is for transmit. Stepper motor. Coming to stepper motor, how it is driven, how it executes, how you write your application. You drive it through GPIO lines, right? So, needless to say, if you want to simulate stepper motor, then you have to play with the virtual registers of that particular port lines to which your stepper motor is connected to. Okay. So, indirectly saying stepper motor can also be simulated. Decision coverage required to run the conditional parts. That's what I'm telling you. MCDC coverage, modified condition and decision coverage is required to ensure even conditional jumps are also executed. In my code coverage, Keil IDE, you saw in the main functions, only 84% of the function was executed. Why? That function has 3 conditional jumps which was not executed. To get it to 100%, we have to see that those conditional jumps are also taken by the process. So that is how it is done. If you modify the condition MC, how do you modify the condition? Through unit test. For unit testing tools, we have many. We are the distributors of Tessie software, which is a unit software module testing tool. Other than that, we have other players in the market like LDRA, we have Parasoft, Cantata, Polyspace. All this does the MCDC as well. Okay. Next. Kumar Swami, or ALP programming, assembly language programming with ARM7 TDMI, Keil tools need to be used with minimum version as per VT syllabus or higher versions of Y plus Keil tool to do ALP programming. Right. Okay. See, for doing the programming of ARM7 TDMI or 2148, which is based on ARM7 TDMI processor core, which is from NXP, a lower end MCU from the NXP, which was the first MCU to come up with the on-chip USB controller. It has a USB peripheral. That was the first MCU from NXP, which has on-chip USB. So for this, you can use MDK 4.74, okay, to develop the program. You can, as per this VTU syllabus, if they're asking version 5.0 plus, then that is not the solution, because 4.7, because version 5 or whatever the latest demo version available on Keil site doesn't support ARM7, ARM9. Because you want for ARM7, no, you please continue to use 4.74. Version 5, version 5, if you have older versions of the software which is less than 5.30, because the latest is 5.36. If you have less than 5.30, then you can still develop the program for ARM7 by downloading the legacy pack support for Keil MTK version. As prescribed by VTO University, you know both hardware and software. Steps of execution necessary. Associate. Chitradurga. Wow. Nice to meet you. Chitradurga is my birthplace. Very good. Thank you. Kumar Swami, you better call me on my number. Okay, we can discuss this. We have a solution, so not an issue for us. I'm sorry, I think I missed your answer. The simulator features available in Keil microvision onwards. No, Christina. Simulation feature is available in all the versions, in all the editions of Keil, from the light version to the professional version, including Essential Plus. So one thing I want to tell here is even if you don't have license also, you can simulate your peripherals. So, but yes, it is limited to core size limitation, 32 KB. What was not showing in your PC?
Hello, I'm Christine. I think the simulator feature was not showing in the Keil which I have. I have the light version only.
Light version, you try to use my for the light version. What version you are using, Christina? On that you have to install legacy pack. Because microvision 5, no simulation support for many devices are not provided.
Oh, okay.
To simulate the device, what you are planning to use, no, you have to first check that whether the device is simulated. If it is simulated, then download the legacy pack.
Oh, okay. Then I'll contact you if I require for the processor which we are working on.
Sure. You can send an email to Geeta@GSASMSPM and my phone number is also.
Sure. Thank you.
Yes, Kumar Swami. Yeah, thank you. Got connected little later, so breaking continuity. Expect to know more details later, madam. Okay. For the benefit of the team, I'll tell this particular webinar is recorded and it will be soon be available on YouTube. And for participants who are registered for this webinar, you will get a link from our team. YouTube link, so you can go out and watch that again. And if you have any questions, you can reach out to my contact details here. The logic analyzer feature that you had demonstrated means a physical USB logic analyzer. No. This logic analyzer is a feature of Keil Simulator. It is there in the. You can see that you can use the logic analyzer along with your hardware. When you use it along with the hardware, you call it as debug because you're loading the code to the hardware and testing the code on the board. You call it as debug word. If you're not connecting hardware, you can still test your program on the logic analyzer, which is simulator. So the idea remains the same for debug and simulator. It depends on what option you select under debug tab.
Oh, okay. Fine. That was my question actually. So, like that whole logic, I think it is related to this which is not available yet in the night. For at least, I cannot see in my laptop because maybe that processor has not been simulated by ARM
That's
yet.
what I'm telling you. If you're not seeing simulation, means you have to see what device you're using, and if any simulation support was provided by Keil, then you have to download the legacy pack.
Okay.
Next
That's all set. That's all set. Thank you.
Yeah. Thank you. Next time we'll try to use laptop or desktop. No issues, Kumar Swami. I understand that you missed my session in starting. You can watch out in the YouTube video link, and I'm sure you'll catch it up. So, any other questions, team? You have it for me. So, if there are no questions, you can always send an email to my Geeta@GSASMSPL email ID, and I'll be glad to answer your questions. You're welcome, Christina. Thank you, Bhuvan. Okay, Abhimanyu, I missed your question. Sorry. Is it possible to show a demo of any communication protocols like UART, SPI, or I2C? UART SPI R2C, yes, I can show, but I don't have the ready-made sample project from Keil directly. I have to modify any of the project and show the simulation, because I have to modify the, I should see that any project we have which is showing UART will be there for sure. But SPI I2C, I'm not sure. Whatever sample project given by it's not there. Because the process, the board, whatever I showed LPC 1168, we do have examples for SPI and I2C. But for that, again, we have to write INI file, virtual registers. To answer your question quickly, I can guide you where you can get this information. Thanks, Irfana, for pointing me to that question. I missed that question. Let me share the browser. Okay, so I2C you are asking, huh? See I2C here. I2C simulation. See, they are given here. We can simulate, we can configure I2C peripheral through this, and we can see I2C communication. We can ourselves enter the I2C data. See if we can get something from out of this. I2C virtual simulation registers. These are the various registers for I2C. Because this is only SDA and clock, only 2 pins, no I2C. So I2C in for simulating any data going out from the master. I2C out. Data coming to master, I2C, I2C out is anything data going out of the master. So similarly, we have for even SPI. So give an example itself. Okay. Let me put this link in the chat window so it will be helpful. So any other questions, team? And if the team has any feedback on my session, or if you're looking for any specific topics, would you like to have a webinar, technical webinar, so feel free to include that in the email. You can send me an email, or you can send it to the email where you'll be getting this information for the YouTube link also. We can give the feedback there. So if you suggest me the topic, it will be helpful. So I can prepare for that, but next month it will be on fixed virtual platform. Laksha Bharadwaj, I have doubt related to my career. Will you guide me? This question I don't know how to answer. Laksha, you can please call on my phone. I'll see how best I can help you. So no other questions for me? Okay. So thanks, team. Thanks for your time and patience in attending to my session. And any questions you have, you can please send me an email, call on my phone. If this particular video will be available on YouTube link. Thanks once again. Have a pleasant day. Take care and be safe.